Hey everyone, in this video I'm going to take you through the different types of acids and then show you how to name each type. There are two types of acids that we have to worry about naming. There are binary acids and there are ternary acids, but I think a better name for those are oxyacids. So most of the time you're going to hear me refer to ternary acids as oxyacids. Let's use the Venn diagram to kind of go through and look at some similarities and differences between the types of acids. So on the left, we'll put information about the binary acids, and on the right about the ternary or oxyacids. But let's start with some things that each type of acid has in common. First of all acids are aqueous. That means they will always have to be AQ when you write them in chemical equations. Acids are all about the ions that are present in solution. Okay, so that's very important. Aqueous, which means they're dissolved in water. Second of all, acids are all built with the same cation, which is the H+. We call that, in acid terminology, usually hydronium. Now, H3O positive is the more correct form of this. In AP chemistry, we'll talk more about the hydronium ion H3O positive. But in pre-AP, we're going to be okay with just doing the H positive. And then the last similarity that I wanted to mention to you is that when you name any acid, the name always ends with the word acid. So that's something you'll see in common with everything. Now let's go back to binary acids and talk about some unique things about binary acids. First of all, binary acids are made from monatomic ions. Monatomic ions. So these are your oxides and sulfides and chlorides and things like that. Another unique thing about binary acids is that every name starts with the prefix hydro. Prefix hydro. So these are your hydrochloric that you've heard of, hydrofluoric, maybe you've heard that. These are all binary acids. You see that prefix. And then finally, they all end with the suffix IC. Every binary acid will end in IC. Now that I've shown you how are some common characteristics of the binary acids, let's name a few. Let's remember that all binary acids and all acids have the H positive ion. Now, if we're binary acids, we start with a monatomic ion. So, for example, if I were to make an acid out of the fluoride ion, putting it with the positive hydrogen ion, I would get an HF formula. And of course, it has to be aqueous. And I would name that hydro and then fluoric. They all have to end in ic. The fluor comes from the monatomic ion, hydrofluoric. Another example very similar to that one would be if I took the bromide ion, bromide, with the H positive with it, we get HBr. Hydro, bromic. Always starts with hydro, always ends with ic, and of course they all end in acid. So hydrobromic acid. The charge really determines how many hydrogens you have. So in this case, we have the oxide ion -2. Therefore, we will need not one hydrogen, but two hydrogens ions to balance the charge. And of course, we call that water. And yes, water is an acid. And this is the exception to the aqueous rule, I guess, because water, of course, is a liquid. Water is very important, and that's a deeper AP topic. If we had nitride ion, you can also make a very weak acid out of this with 3 hydrogens and we would call that hydronitric acid, which is kind of weird, and I think it has a more common name also. Now let me show you one exception to this, and that is Cn minus. This is called cyanide ion. We're still going to call this a binary acid, and the reason why is because this polyatomic ion doesn't have oxygen in it, so it's not one of those oxy anions like I mentioned a few minutes ago. But it all works the same. If it's a -1, I put 1 hydrogen in front, we get HCN, and the rules for naming apply. Hydrocyanide becomes cyanic, hydrocyanic acid. All right, let's revisit real quickly ternary acids. Okay, so some common things about these ternary or oxy acids is that they are made from the polyatomic ions. Something you're going to like about these, I think, is that they have no prefix. If the polyatomic ion already has a prefix, so let's go ahead and make that improvement here. No new prefix. If the polyatomic already has a prefix such as per, as in perchlorate, or hypo, or even thio, we're going to keep those. We're not going to do any changing to the prefixes that are already there. We're just not going to add a new one like hydro. And the really unique thing about the oxy acids is that the suffix has some variety. If the polyatomic ion ends in ate, like sulfate, nitrate, you're going to replace that and use ic, the same ic that we use for binary. If, however, the polyatomic ends in ite, such as sulfite, nitrite, chlorite, we're going to use the prefix, or to replace it with the prefix ous, us, such as nitrous acid or sulfurous acid. All right, let's scroll down here and add a few examples of ternary or oxy acids. Remember, still H plus is our cation. So one example would be if I took nitrate, NO3 minus, I would need 1 hydrogen to balance that charge, so we'll get HNO3. Of course, it still has to be aqueous, and we would call that nitric. Nitrate becomes nitric. Another example, if I have carbonate, which is -2, now I would need 2 hydrogens to balance the charge, CO3, and it's aqueous. Carbonate is my ion, so the name of this acid would be carbonic acid. 8 becomes ic, carbonic acid. Let's try a different suffix here. Let's take the polyatomic ion phosphite, not phosphate, but phosphite. To make the formula, I need 3 hydrogens to balance the charge. Now, phosphite is going to become phosphorus. It's a little bit strange because this is unique to just phosphorus and sulfur, that the root word kind of expands as you take the ite away. But ite becomes us, so this would be phosphorus acid. A cleaner example of that would be if I took NO2 minus, which is nitrite, HNO2. Of course, it would be aqueous. Now that's nitrite, that just becomes an even swap nitrite, nitrous acid. And you can do this in front of any polyatomic ion, even ones that you don't normally hear of. Like here is chromate with a -2 charge. If I put a couple of hydrogens in front of that to balance the charges, make it aqueous, that becomes chromate, becomes chromic acid. All right, now that we've got some of the basics down, let's go through and do a little practice here. You can see from this list of acids, I didn't write aqueous next to each one because we're going to take that for granted. And then notice that hydrogen is in front of everything, so that's a very good visual clue for now that you're dealing with acids. When you want a name, you first have to classify each acid as either binary or ternary / oxy acid. Then you'll know which naming system to use. So let's go through here and do that. HCl, I only see 2 elements, no oxygen, so this is going to be a binary acid. In part B, same conditions, binary acid. In C, 2 elements, only 2 letters, that's even easier, binary acid. And the same with D. E is a little trickier. HCN, there's 3 elements there, there's no denying that, but it's not a ternary acid because it doesn't have the oxygen. So even though there's 3 elements here, this is going to be the binary exception that I showed you earlier. Now, a quick glance at all the other ones starting with F, they have oxygen in them. So therefore, those are, and 3 elements, so those are going to be ternary acids. Now, just to keep it simple, I'm going to just call them ternary here because T is obviously different when I write on this board than the B. So, different types of acids. So let's name A through E according to the rules I taught you for binary acids. HCl, we know these all start with hydro, so this is going to be hydro. The root here is the ion, not polyatomic, but monatomic chlorine, so this is chlor. Chloride becomes ic, they all end in ic, and so then we would add the word acid, hydrochloric acid. Now, to save space as we continue, I'm not going to write the word acid each time. Just understand that each one of these would end in acid. Let's go through these a little quicker. Hydro, because it's binary. Bromine, so we'll use the root word brome, and then end it with the ic, hydrobromic acid. C is one of our favorites, hydro. Iodine, the root word is iode, and then we end it with ic, hydroiodic, or some people call it hydroiodic. And then finally, D, hydrofluorine is fluor, and we add ic. The ic is actually replacing ide in the monatomics. E is our last binary. Remember, it's the exception, so it's still hydro. Cyanide becomes cyan. Ide becomes ic. All right, starting with F, we have a bunch of oxyacids. These do not have the prefix, so we just go right to identifying the polyatomic. This is nitrite, okay? So the root is nitra. Ite becomes OUS, nitrous acid. We'll write the word acid on the first ternary acid here. So nitrous acid. Let's go to G. SO4 is sulfate. So the root, I mentioned on the previous screen that sulfur and phosphorus kind of expand when they change. So instead of just sulfur, we're going to expand it to sulfur. 8 becomes ic. So sulfuric acid. H, we have PO4. I hope you identified that as phosphate. So again, phosphorus is kind of weird in that it expands back to the phosphor root. 8 becomes ic, phosphoric acid. I, we have SO3, which is sulfite. So again, sulfur kind of expands back to full form. Ite becomes OUS, sulfurous acid. Now J, K, and L are all very similar. This is the group of the chlorine oxyanions. Let's actually, let's go ahead and go in the order it's written, J. ClO3 is chlorate. So the root there is an easy chlor. Now the rule says 8 becomes ic, so chloric acid. That is something students miss a lot because you just hear that chloric and you want to put a hydro in front of it. But as you can see here, there is already a formula and a way to name and distinguish hydrochloric. It's binary. If it's just chloric, it's oxy. Now K has something important. It's still very similar to part J, but ClO4 is not chlorate, it's perchlorate. So we're not going to drop that prefix. We're going to do instead perchlor, and then just change the suffix. Ate becomes ic. So perchloric acid, not just chloric acid. And then for L, we have chlorite. So the root again is chlor. Ite becomes OUS, chlorous acid. So that's how you name acids. In summary, it's important to identify the type of acid that you're dealing with. Each type of acid has its own naming rules. So know your naming rules and then practice. If you have any questions, come and see me.